Tonight, we drift toward a quiet moon orbiting Jupiter, Europa. At first glance, it appears cold and still, sealed beneath the shell of ice. Yet beneath that frozen surface, a vast ocean moves slowly in darkness, shaped by gravity, pressure, and time. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. Europa does not look dramatic at first glance. It appears small, pale, and quiet, moving steadily around Jupiter at a distance of about 670,000 kilometers. Its surface reflects light softly, covered almost entirely in ice. Nothing about its appearance suggests abundance. And yet, beneath that frozen shell, Europa contains more liquid water than all of Earth's oceans combined. This idea began to take shape in the late 20th century, when spacecraft observations revealed something unexpected. Europa's surface is smooth compared to rocky worlds. Large impact craters are rare. Instead, the ice is crossed by long, dark lines that stretch for thousands of kilometers. These lines resemble cracks in ice on a frozen lake after seasonal movement. On Earth, such patterns form when ice floats on liquid water and shifts under stress. Further clues came from gravity and magnetic measurements. Europa moves through Jupiter's powerful magnetic field. Instruments detected subtle changes in that field near the Moon, changes that are best explained by a global layer of salty liquid water beneath the ice. Salt conducts electricity, but ice does not. This distinction matters significantly at a planetary scale. The numbers involved are calm, but astonishing. Europa's ocean is estimated to be around 100 kilometers deep. In contrast, Earth's average ocean depth is less than 4 kilometers. Even though Europa is smaller than Earth, its hidden ocean wraps around the entire Moon, forming a global layer. If that water were brought to the surface, its volume would exceed that of Earth's oceans combined. In daily life, water is something poured into a glass or heard running through pipes. Its presence feels ordinary, but on Europa, water exists in silence and darkness, sealed away from sunlight by thick ice. Yet, it remains active. The ice shell shifts. Heat flows upward from the interior. The ocean responds slowly, steadily, over millions of years. This redefines how water is understood in the universe. On Earth, liquid water sits openly on the surface, shaped by atmosphere and sunlight. Europa shows a different arrangement. Water can exist hidden, protected, and long-lasting, even far from the sunday. Europa does not display its abundance. It carries it quietly. A small moon, orbiting a giant planet, holding a volume of water that reshapes expectations about where oceans can exist and how common they might be beyond Earth. Europa's surface forms a calm, frozen boundary. Beneath it, the structure of the Moon unfolds in layers, each playing a quiet role in shaping its hidden ocean. From the outside, the ice appears solid and motionless. On the inside, it behaves more like a slow-moving shell. The outermost layer is ice, likely several tens of kilometers thick. This ice is not uniform. Near the top, it remains brittle and cold, similar to ice that forms on a winter lake. Deeper down, pressure and heat soften it. The ice begins to deform rather than crack, flowing gradually over long periods of time. This transition matters. It allows surface features to shift without shattering completely. Below the ice lies a global ocean of liquid water. Estimates place this ocean at roughly 100 kilometers deep. The water is likely salty, similar in composition to Earth's oceans. Salt lowers the freezing point of water and helps keep the ocean liquid despite Europa's distance from the sunlight. The ocean exists in complete darkness, insulated from space by ice and warmed from below. At the center of Europa sits a rocky interior. This core provides heat through radioactive decay and tidal friction. As Europa orbits Jupiter, gravity stretches and relaxes the moon slightly, over and over again. This repetitive motion generates internal heat, much like bending a metal wire slowly warms it. Over millions of years, this process supplies enough energy to prevent the ocean from freezing solid. The boundary between rock and water may be one of the most active regions on the moon. On Earth, similar environments exist at deep-sea hydrothermal vents. There, chemical reactions occur without sunlight, driven by heat and minerals. Europa's ocean floor could host comparable processes operating silently beneath kilometers of water and ice. This layered structure explains Europa's unusual surface. The cracks and ridges above reflect movement below. Ice shifts because water moves. Heat rises because gravity supplies energy. Nothing happens quickly, but nothing is truly still. Europa's frozen surface is not an endpoint. It is a lid. Beneath it, a complex interior continues its slow interaction between ice, water, and rock, shaping one of the most intriguing hidden environments in the solar system. Europa's ocean was not discovered by a photograph. No camera has looked beneath its ice. Instead, its presence was inferred through motion, measurement, and subtle physical effects that unfold quietly over time. One of the first clues came from Europa's surface. The ice is unusually young and smooth. Large impact craters are scarce, suggesting that old features are erased. On Earth, a frozen surface can be renewed when ice floats on liquid water and slowly rearranges itself. The long bands and intersecting ridges on Europa resemble this kind of renewal, as if the surface has been gently reset again and again. Stronger evidence emerged from magnetic measurements. In the late 20th century, spacecraft instruments detected changes in Jupiter's magnetic field as Europa passed through it. Europa does not generate its own magnetic field. Even so, the field around it shifted in a patterned way. The simplest explanation is a conductive layer beneath the surface. Salty liquid water conducts electricity. Solid ice does not. This distinction allowed scientists to infer a global ocean without direct observation. Gravity offered another confirmation. As spacecraft flew past Europa, tiny changes in speed revealed variations in mass beneath the surface. These variations match a layered interior with a dense rocky core, a thick shell of ice, and a large volume of liquid water in between. The data fit together quietly, like pieces settling into place. An everyday comparison helps clarify this method. A person can tell whether a cup is full by feeling its weight, even without looking inside. In a similar way, Europa's gravity and magnetic responses reveal what lies beneath its frozen exterior. None of this required drilling through ice or touching the ocean itself. The moon's behavior spoke on its behalf. Its orbit, its surface patterns, and its interaction with Jupiter's magnetic environment all point toward the same conclusion. Europa's ocean is known not because it is seen, but because it leaves consistent traces in how the moon moves, responds, and slowly reshapes itself. In planetary science, absence of sight does not mean absence of evidence. Europa holds its importance quietly. It does not dominate its surroundings like Jupiter, nor does it display dramatic features like towering volcanoes or thick clouds. Its significance comes from a rare combination of conditions that exist together in a stable, long-lasting way. First, Europa has liquid water, not a temporary melt or a shallow layer, but a global ocean that has likely existed for millions of years. Longevity matters in planetary science. Short-lived environments fade before complex processes can develop. Europa's ocean is protected beneath ice, shielded from radiation and surface chaos, allowing it to persist. Second, Europa has energy. Although it receives little sunlight, it is not cold inside. As it orbits Jupiter, powerful tidal forces flex the moon repeatedly. This motion generates heat through friction, the same way bending a material slowly produces warmth. That internal energy keeps water liquid and drives movement within the ice and ocean. Third, Europa has chemistry. Its ocean is thought to be salty, and its rocky interior may supply minerals to the water above. On Earth, interactions between water and rock create chemical gradients that support complex systems. These interactions do not require sunlight. They require time, heat, and contact between materials. What makes Europa especially important is that these three elements, water, energy, and chemistry, exist together in one place. Many worlds have one or two of these features. Few appear to have all three in balance. Europa also reshapes priorities in exploration. For much of the 20th century, planets were the main focus. Moons were considered secondary. Europa helped change that perspective. It showed that small worlds, when placed in the right gravitational environment, can host conditions once thought unique to planets. In everyday terms, Europa is like a quiet room in a busy building. Nothing about it draws attention at first. Yet inside, essential processes continue steadily, unnoticed from the outside. Europa's importance lies not in what it displays, but in what it sustains. A stable ocean, hoarded by gravity, protected by ice, existing far from the warmth of the sun, expands the definition of where complex environments can exist in the solar system. Europa presents a simple contrast. Its exterior is frozen solid, while its interior remains fluid and active. This arrangement defines the moon more than any single surface feature. The ice shell acts as both barrier and protection. On the surface, temperatures remain far below freezing, and radiation from Jupiter constantly strikes the ice. The shell absorbs this harsh environment, shielding what lies below. Much like insulation in a house during winter, thick ice slows the loss of internal heat, keeping the deeper layers stable over long periods of time. Beneath this shell, liquid water persists. The ocean does not freeze because heat rises from the interior and because salt lowers water's freezing point. These two factors work together quietly. The result is an ocean sealed away from space, unaffected by day or night, season or sunlight. This structure is not unique to Europa alone, but Europa provides one of the clearest examples. The separation between surface and interior allows each layer to behave differently. Ice fractures and shifts slowly. Water circulates beneath it. Rock interacts chemically at the ocean floor. Each layer influences the others without direct exposure. A familiar example helps ground this idea. Ice-covered lakes on Earth often remain liquid underneath throughout winter. Fish continue to move, water continues to circulate, and life persists below a frozen surface. Europa follows this same principle, scaled up to a global level and sustained over geological time. The boundary between ice and ocean is not static. Heat causes melting in some regions and refreezing in others. Over millions of years, this process reshapes the surface above. The cracks and ridges visible from space are records of activity below, translated slowly through ice. Europa's identity lies in this division. A quiet, frozen exterior conceals an active interior. The contrast allows complex processes to continue undisturbed, hidden beneath ice, steady and persistent. Ice on the outside, ocean on the inside. A simple structure, repeated consistently, holding one of the most stable, hidden oceans known in the solar system. Europa's ice shell is not a thin crust. It is a deep, layered structure that separates the surface from the ocean below. Estimates suggest this shell may be tens of kilometers thick, forming one of the most important boundaries in the solar system. Near the surface, the ice behaves rigidly. It fractures under stress, creating long cracks and intersecting lines. These features remain visible because temperatures are extremely low and change very little. Radiation from Jupiter alters the surface chemically, darkening the ice over time, but the structure itself stays solid. Deeper within the shell, conditions change. Pressure increases, and ice begins to soften. Instead of breaking, it slowly deforms, flowing over long time scales. This type of ice behaves less like glass and more like thick wax. It moves quietly, measured not in days or years, but in thousands or millions of years. This layered behavior allows the shell to act as a seal. Heat from below rises gradually. Cold from above presses downward. Between them, the ice adjusts, preventing the ocean from escaping, while also preventing complete freezing. The shell regulates exchange without allowing chaos. A familiar comparison exists on Earth. Glaciers appear solid and unmoving, yet they flow slowly downhill under their own weight. Europa's ice shell functions in a similar way, though on a global scale and in far colder conditions. The thickness of the shell matters for more than structure. It shields the ocean from radiation and surface impacts. It also limits direct contact with space, preserving stable conditions below. At the same time, fractures and warmer regions may allow limited interaction between surface materials and the ocean, transporting chemicals downward over time. The ice shell is not simply a barrier. It is an active system, balancing heat, pressure, and motion. It keeps Europa's ocean hidden, contained, and remarkably stable. By sealing liquid water beneath solid ice, Europa demonstrates how an ocean can survive in an environment that appears frozen and inert from the outside. Europa remains warm inside, not because of sunlight, but because of gravity. As the moon travels around Jupiter, it is constantly pulled and released by the giant planet's immense mass. This repeating stretch is known as tidal force, and it acts like a slow, steady engine deep within the moon. Europa's orbit is slightly elongated rather than perfectly circular. Because of this, the strength of Jupiter's pull changes as Europa moves along its path. The moon is gently squeezed and relaxed again and again. This motion is subtle, but it never stops. Over time, it generates heat through internal friction. A simple, everyday example helps clarify this process. When a metal paperclip is bent back and forth slowly, it begins to feel warm. The heat does not come from the air or from fire. It comes from resistance inside the material itself. Europa experiences a similar effect, scaled up to a planetary level and sustained for millions of years. This tidal heating prevents the ocean beneath Europa's ice from freezing solid. It also keeps the ice shell above in motion, allowing cracks to open, shift, and slowly close. Without this gravitational energy, Europa would become a frozen, inactive world. The influence of neighboring moons plays a role as well. Europa's orbit is stabilized by a gravitational rhythm shared with Io and Ganymede. This arrangement maintains the slight orbital stretching that allows tidal heating to continue. The system remains balanced, neither collapsing into stillness nor escalating into instability. Tidal forces operate quietly. They do not create sudden eruptions or visible storms on Europa's surface. Instead, they supply a gentle, continuous flow of energy. Heat rises, ice adjusts, water circulates below. Europa's warmth is not accidental. It is the result of motion, gravity, and repetition. Far from the sun, the moon stays active because it never fully rests within Jupiter's grasp. Cracks, lines, and moving ice plates. Europa's surface is marked by long, dark lines that cross and intersect in complex patterns. These features do not rise like mountains or sink like craters. They stretch, curve, and reconnect, suggested motion rather than impact. The ice records change in a quiet, readable way. These lines form as the ice shell responds to stress. Tidal forces gently flex the moon, opening fractures near the surface. Some cracks widen, others shift sideways, and many slowly heal as warmer ice rises and refreezes. The process resembles a frozen roadway that splits in winter, then partially reseals as temperatures fluctuate, leaving scars that trace past movement. In several regions, blocks of ice appear to have separated and rotated before settling back into place. The shapes fit together like pieces of a broken plate that drifted slightly before stopping. This behavior indicates that the ice floats on a softer layer below. On Earth, sea ice can fracture into large sheets that move independently when water lies beneath them. Europa shows a similar pattern, expanded across an entire moon. The motion is extremely slow. Ice plates shift over thousands to millions of years. There is no sound, no sudden collapse. Stress builds, releases, and redistributes. Each cycle leaves a line, a ridge, or a band that remains visible long after the motion itself has passed. Some lines appear darker because material from below has risen to the surface. Salts and other compounds carried upward by warmer ice alter the color of the surface slightly. This exchange does not require open water at the top. It occurs through fractures and gradual deformation within the shell. The overall result is a surface that looks young and active despite the cold. Old features are erased as ice moves and reforms. New ones appear as stress continues. The surface becomes a map of internal behavior, drawn slowly and rewritten repeatedly. Europa's cracks and shifting plates do not signal destruction. They reveal a system in balance, where ice responds to energy without breaking apart entirely. The moon's surface remains intact, while quietly reflecting the motion of an ocean hidden far below. Europa's ocean exists without light. Beneath kilometers of ice, no sunlight reaches the water below. Day and night have no meaning there, yet the ocean is not inactive. It is shaped by chemistry, pressure, and slow circulation. The water is thought to be salty. This conclusion comes from multiple lines of evidence, including magnetic measurements and surface composition. Salt lowers the freezing point of water, helping the ocean remain liquid. It also allows the water to conduct electricity, which explains how Europa interacts with Jupiter's magnetic field. In planetary science, salt is not a detail. It is a stabilizing factor. On Earth, salty oceans behave differently from freshwater lakes. Salinity affects density, circulation, and how heat moves through water. Europa's ocean likely follows similar physical rules, even though the environment is far more extreme. Warmer water may rise slowly, while colder, denser water sinks, creating gentle circulation over vast timescales. Darkness does not mean absence of energy. Heat from Europa's rocky interior flows upward into the ocean. At the boundary between rock and water, chemical reactions may occur. On Earth, comparable environments exist at the deep ocean floor, where hydrothermal systems operate without sunlight. These systems rely on heat and chemistry rather than light. An everyday comparison helps ground this idea. A thermos can keep liquid warm and stable without external heat or light, simply by limiting exchange with its surroundings. Europa's ice shell performs a similar function, insulating the ocean and preserving internal conditions. The absence of light changes the rhythm of the environment. There are no seasons, no surface weather, no sudden temperature shifts. Conditions remain steady over long periods. This stability allows chemical processes to persist without interruption. Europa's ocean remains hidden, dark, and sealed. Yet it is not empty. It is structured, dynamic, and shaped by forces that operate quietly beneath ice. In the absence of light, other forms of activity continue, steady and uninterrupted, within one of the solar system's most isolated oceans. Europa does not generate its own magnetic field. Unlike Earth, it has no internal dynamo producing a steady magnetic signature. And yet, when spacecraft passed near the Moon, instruments detected magnetic behavior that could not be ignored. Europa travels through Jupiter's immense magnetic environment. As it moves, the surrounding magnetic field changes slightly. Measurements showed that these changes were not random. They followed a consistent pattern, synchronized with Europa's position and motion. The Moon appeared to respond to the magnetic field rather than create one. This response is best explained by induction. When a conductive material moves through a changing magnetic field, electrical currents are generated within it. Those currents, in turn, produce a secondary magnetic signal. On Earth, this principle is used in everyday technology, from electric generators to wireless charging pads. Movement and conductivity are enough. A built-in magnet is not required. For Europa, the conductive material is most likely salty liquid water. Ice alone cannot produce this effect. Solid rock cannot either, at the scale observed. A global layer of electrically conductive ocean fits the data precisely. The strength, timing, and orientation of the detected signals align with what physics predicts for a subsurface ocean. These magnetic clues were recorded in the late 20th century and refined through repeated flybys. Each pass added confidence, not through dramatic discovery, but through consistency. The same signals appeared again and again, unchanged in character. A simple comparison helps clarify the method. A person does not need to see wiring inside a wall to know electricity is flowing. The hum of a device or the warmth of a surface is enough. In the same way, Europa's magnetic response reveals activity beneath its ice. The absence of a native magnetic field makes the evidence stronger, not weaker. Without an internal magnet to confuse the signal, the induced response stands out clearly. Europa's ocean announces itself quietly, not through light, not through sound, but through a subtle interaction with invisible fields. In planetary science, magnetism becomes a language, and Europa speaks it with precision. Europa and Earth share a simple connection. Both are worlds shaped by liquid water, orbiting the same Sunday. The similarity ends quickly when their environments are compared, yet the presence of water places them in the same physical category. On Earth, water lies open to the sky. Oceans respond to sunlight, wind, and atmosphere. Day and night drive surface temperatures. Seasons redistribute heat. Rivers and clouds connect sea, land, and air in visible cycles. These processes are familiar because they are experienced daily. Europa organizes water differently. Its ocean is hidden beneath ice, separated from sunlight and weather. The sun still matters, but indirectly. Its gravity holds the solar system together, while Jupiter's gravity supplies the energy Europa needs. Water on Europa is controlled by internal heat and pressure rather than climate. Despite these differences, the physics of water remains the same. Liquid water flows, mixes, and transports heat. Salts dissolve and affect density. Temperature differences drive circulation. These rules apply whether water rests under open skies or beneath kilometers of ice. Earth provides a reference point. Studies of polar ice sheets and subglacial lakes show that liquid water can persist beneath thick ice for long periods. In Antarctica, lakes remain sealed below ice, yet stay stable, influenced by geothermal heat and pressure. Europa represents this arrangement on a planetary scale. The shared reliance on water links Earth and Europa across distance. One world displays water openly, the other conceals it completely. Both demonstrate that water does not require a narrow set of surface conditions to exist. In practical terms, this comparison reshapes how water is recognized beyond Earth. It is no longer limited to blue surfaces and reflective oceans. It can be present without visibility, sustained by gravity and internal energy. Europa and Earth orbit the same star, but their water tells two different stories. Together, they show that a single physical substance can organize a world in more than one stable way. For most life on Earth, sunlight sets the rhythm. Plants grow by converting light into energy, and food chains build upward from that process. This pattern feels fundamental, but it is not universal. Far below the ocean's surface, sunlight disappears completely. In these depths, darkness is permanent, pressure is immense, temperatures are low, except where heat escapes from the planet's interior. Yet, life persists. In the late 20th century, deep-sea exploration revealed ecosystems clustered around hydrothermal vents on the ocean floor. These vents release heated, mineral-rich water from cracks in Earth's crust. Instead of relying on sunlight, microorganisms use chemical energy from these minerals. This process, known as chemosynthesis, converts chemical reactions into usable energy. From these microorganisms, entire communities form. Larger organisms depend on the chemical energy captured at the base of the system. The environment remains stable for long periods because the heat source comes from within the planet rather than from changing surface conditions. An everyday comparison helps ground this idea. A building can remain warm through internal heating, even when the outside temperature drops. The warmth does not depend on the sun at that moment. It depends on energy generated and circulated inside. Deep ocean ecosystems function in a similar way, insulated from surface change. These environments matter when considering Europa. Its ocean receives no sunlight. Just like Earth's deep sea, heat and chemical interactions likely occur at the boundary between rock and water. If similar reactions take place, energy could be available without light. The lesson from Earth is not that life exists everywhere darkness does. It is that darkness alone does not prevent complex systems from forming, where water, energy, and chemistry intersect. Activity can continue quietly. Earth's deep oceans show that life can organize itself far from light, sustained by internal processes. This expands the range of environments considered physically capable of supporting complex behavior beneath ice and water. Europa's ocean brings together several conditions that, on Earth, are associated with active systems. Liquid water is present. Energy is supplied from below. Chemical materials are likely available through contact between water and rock. These elements do not guarantee life, but they define an environment that is physically capable of sustaining organized processes. The ocean is sealed beneath ice, creating stability. Temperatures change slowly. There are no storms, no surface seasons, and no rapid shifts driven by sunlight. Over long periods, this steadiness allows chemical reactions to proceed without interruption. In planetary systems, stability often matters as much as energy itself. At the base of the ocean, the rocky interior may interact directly with liquid water. Heat from tidal forces could drive reactions between minerals and water, releasing chemical energy. On Earth, similar reactions occur in deep marine environments and support complex microbial communities without light. Europa's salinity also plays a role. Salt affects how water circulates and how heat is distributed. Slow circulation can transport energy and chemicals across large distances, preventing isolation of active regions. This allows the ocean to behave as a connected system rather than a collection of stagnant pockets. An everyday analogy helps clarify this structure. A well-insulated building with internal heating can maintain comfortable conditions throughout its interior, even when the outside environment is extreme. Europa's ice shell acts as insulation, while tidal heating supplies internal energy. There are also limitations. Europa's ocean may lack certain elements found abundantly on Earth's surface. Exchange between the ocean and the surface is restricted by thick ice. These factors introduce uncertainty rather than contradiction. Considering all evidence together, Europa's ocean appears capable of supporting organized, energy-driven systems under the right conditions. Whether such systems exist remains unknown. What is clear is that the environment itself does not prevent them. Europa demonstrates that support for complex behavior does not require open skies or sunlight. It requires water that remains liquid, energy that continues to flow, and chemistry that can operate over long timescales. In planetary science, water holds a unique position. It is not rare by itself, but its behavior is unusual. Water remains liquid across a wide range of temperatures, dissolves many substances, and transports heat efficiently. These properties allow it to support complex, long-lasting processes. On Earth, water acts as a medium rather than a participant. Chemical reactions occur within it, heat moves through it, and materials are carried across large distances. This role makes water less visible than fire or light, yet more influential over time. Systems organized around water tend to persist rather than fluctuate. The search for life changed direction as this understanding developed. Early exploration focused on finding Earth-like surfaces and atmospheres. Over time, attention shifted toward environments where liquid water could exist in any form. This shift expanded the range of worlds considered physically capable of supporting complex systems. Water also buffers change. It absorbs heat slowly and releases it gradually. This moderates temperature extremes and creates stable internal environments. On Europa, water is protected beneath ice, isolated from rapid external variation. Stability becomes a defining feature rather than an accidental one. An everyday comparison helps clarify this effect. A large body of water warms and cools more slowly than dry land. This is why coastal regions experience milder temperatures. The same principle applies at planetary scale, where water smooths extremes and extends usable conditions over time. Europa demonstrates how water reshapes priorities. The Moon does not resemble Earth's surface, yet it contains one of the largest oceans in the solar system. Its value lies not in appearance, but in physical capability. Water changes the search for life by shifting attention away from visible similarity and toward internal structure. It allows environments to function quietly, shielded from external chaos, sustained by slow and consistent energy flow. In this context, Europa is not important because it looks familiar. It is important because it shows how water can organize a world in ways that remain hidden, stable, and physically viable, far from traditional expectations. Long before Earth developed continents, forests, or an oxygen-rich atmosphere, it was a very different world. Its surface was unstable, shaped by heat from within and frequent impacts from space. Water existed early, but conditions on the surface were harsh and constantly changing. During this early period, much of Earth's activity took place below the surface. Heat flowed upward from the interior. Water interacted with rock. Chemical reactions occurred in protected environments, shielded from the chaos above. These settings were stable, not because they were calm, but because they were insulated. Europa reflects aspects of this ancient arrangement. Its ocean is hidden beneath ice, separated from radiation and surface disruption. Energy rises from the interior through tidal heating rather than radioactive decay alone. Water and rock remain in long-term contact, allowing chemical processes to continue without interruption. The comparison is not exact. Early Earth had a thinner crust and a different composition. Sunlight played a larger role near the surface. Europa's environment is colder and more isolated. Still, both worlds share a reliance on internal energy and protected water. On Earth, environments similar to these ancient conditions still exist. Deep beneath the ocean, water circulates through rock, driven by heat and pressure. These regions preserve processes that began billions of years ago and continue today, largely unchanged by surface evolution. An everyday analogy helps clarify this parallel. A building under renovation may appear chaotic on the outside, while essential systems continue operating in protected interior spaces. Early Earth and Europa both emphasize the importance of what happens away from the surface. Europa does not recreate Earth's past. It offers a simplified version of some of its foundational conditions. By studying Europa, scientists gain insight into how water, energy, and chemistry may have interacted before Earth became the world it is now. In this way, Europa acts as a quiet reference point, not a copy of early Earth, but a reminder that complex planetary processes often begin beneath the surface, hidden, stable, and shaped by internal forces rather than external appearance. For decades, Europa was understood only through distant observation. Flybys provided clues, but direct contact remained out of reach. In the early 21st century, this began to change as missions were designed specifically to approach the moon with focused intent. Modern exploration does not begin with drilling or landing. It begins with careful mapping. Spacecraft are planned to pass repeatedly over Europa's surface, measuring ice thickness, surface composition, and subtle variations in gravity and magnetism. Each pass refines understanding without disturbing the environment. These missions are designed to study the ice shell as an interface rather than a barrier. Instruments analyze fractures, ridges, and regions where warmer ice may be closer to the surface. Areas of recent resurfacing are of particular interest, as they may reveal materials transported upward from the ocean below. The approach mirrors everyday caution. A doctor does not begin with invasive procedures. Observation comes first, guided by non-invasive tools that reveal structure beneath the surface. Europa's exploration follows the same philosophy, scaled to a planetary level. Radiation presents a challenge. Jupiter's magnetic environment exposes Europa's surface to intense particle bombardment. Spacecraft systems are designed with shielding and limited exposure times, allowing precise measurements while minimizing risk. Exploration proceeds in controlled steps. Future concepts extend beyond orbit. Landers and probes have been studied as long-term possibilities, intended to analyze surface ice directly. These ideas emphasize restraint. Any contact must preserve the integrity of Europa's environment while expanding knowledge of its composition and behavior. What makes these missions significant is not speed or spectacle, it is proximity. For the first time, instruments are positioned to study Europa's ice as a dynamic boundary shaped by forces below. As exploration advances, Europa's icy surface becomes a point of contact between distant observation and direct measurement. The goal is understanding gained gradually through touch that is careful, limited, and informed by decades of prior study. For much of human history, Earth's oceans defined abundance. They covered most of the planet's surface, regulated climate, and shaped the development of life. From this perspective, Earth appeared exceptional, even singular, in its relationship with water. As exploration expanded beyond Earth, that sense of scale began to change. Worlds like Europa revealed that large volumes of liquid water can exist far from Earth and far from the Sunday. Europa's ocean alone may contain more water than all of Earth's oceans combined, hidden beneath ice rather than spread across the surface. This shift is not only about quantity, it is about distribution. Earth concentrates water on the surface, where it interacts with atmosphere and light. Europa distributes water internally, sealed away and protected. Both arrangements are stable, but they operate on very different scales and timescales. When additional icy moons are considered, the picture grows larger. Several worlds in the outer solar system are believed to host subsurface oceans. Each adds volume, depth, and variation to the inventory of liquid water beyond Earth. Earth remains familiar, but no longer represents the upper limit. An everyday analogy helps clarify this change in perspective. A person standing beside a lake may believe it is vast until viewing an entire system of lakes connected underground. The original body of water does not shrink, but its context expands. Earth's oceans retain their importance, yet they become part of a much broader pattern. This expanded view alters how Earth is perceived. Its oceans are shallow compared to the depths suggested elsewhere. Its surface exposure makes it dynamic, but also vulnerable to rapid change. In contrast, subsurface oceans emphasize insulation and longevity. Europa contributes to this reframing quietly. It does not challenge Earth by resemblance, but by scale. By existing as a water-rich world without visible seas, it reduces the sense of isolation once associated with Earth's oceans. In a universe where water can be hidden, layered, and extensive, Earth becomes smaller in context, not in value. Its place is defined not by exclusivity, but by participation in a wider, water-shaped architecture of planetary systems. Europa does not exist in isolation. As knowledge of the outer solar system expanded, it became clear that several moons may host liquid water beneath their surfaces. Together, these bodies form a category known as ocean worlds. These worlds share a common structure. Solid ice seals liquid water below, while internal energy prevents freezing. The source of that energy varies. In some cases, tidal forces dominate. In others, radioactive heat contributes. The result is a collection of environments that look frozen from the outside but remain active within. Europa stands out for its balance. Its ocean appears to be deep, global, and in contact with a rocky interior. Some ocean worlds may contain water trapped between layers of ice, limiting interaction with rock. Others may have oceans that are thinner or chemically simpler. Europa's configuration places it near the center of this spectrum. Comparison sharpens understanding. By studying differences among ocean worlds, scientists learn which factors matter most. Ocean depth, salinity, heat flow, and contact with rock all influence how water behaves over time. Europa serves as a reference point against which other subsurface oceans can be measured. An everyday comparison helps clarify this role. In a group of cities, one may not be the largest or oldest, but it becomes important because its infrastructure is well balanced. It connects systems rather than specializing in extremes. Europa occupies a similar position among ocean worlds. The growing list of ocean worlds reduces the sense of rarity once associated with subsurface oceans. Liquid water beneath ice appears to be a repeating outcome of planetary formation when the right conditions align. Europa's significance deepens within this context. It is not valuable simply because it has an ocean, but because its ocean reflects a combination of features that may be common beyond Earth. Among the solar system's ocean worlds, Europa represents a stable midpoint, neither extreme nor marginal. It illustrates how water, energy, and structure can coexist quietly beneath ice across many worlds. For much of modern astronomy, habitability was defined by surface conditions. A stable atmosphere, moderate temperatures, and access to sunlight formed the core assumptions. Worlds were evaluated by how closely they resembled Earth's exterior. Europa challenges this framework without opposition or spectacle. Its surface is cold, airless, and exposed to radiation. By traditional standards, it appears uninhabitable. Yet beneath that surface, conditions change completely. Liquid water persists, energy flows steadily from within, chemical interactions continue over long periods of time. This contrast forces a shift in definition. Habitability no longer refers only to what exists on the surface. It includes internal environments that remain stable and active, even when the exterior appears hostile. Europa demonstrates that a world can support complex conditions without displaying them openly. Quietness becomes an advantage. Without weather, erosion, or rapid temperature swings, Europa's interior avoids constant disruption. Processes unfold slowly. Heat is distributed gradually. Chemical systems have time to establish balance. Stability replaces visibility as the key factor. An everyday analogy helps clarify this idea. A data center may appear unremarkable from the outside, yet inside it maintains tightly controlled conditions essential for continuous operation. Europa functions in a similar way. Its most important activity occurs out of sight, protected by layers designed by physics rather than intention. This revised view of habitability extends beyond Europa. Other ocean worlds may share similar internal stability, despite extreme surfaces. The absence of familiar signs does not imply the absence of viable environments. Europa's contribution is subtle but decisive. It removes habitability from appearance and relocates it within structure, energy, flow, and time. A world does not need to look alive to maintain the conditions that allow complex systems to persist. In redefining habitability, Europa introduces a quieter standard, one based not on surface comfort, but on the long-term coexistence of water, energy, and chemistry beneath protective layers. If life exists beyond Earth, the discovery would not arrive as a dramatic moment of contact. It would emerge through measurements, patterns, and consistency. Chemistry behaving in ways that resist randomness. Energy flowing through organized systems over long periods of time. The meaning of such a discovery would extend beyond biology. It would reshape how life itself is understood. Life would no longer be a singular outcome tied to Earth's specific history, atmosphere, or surface conditions. It would become a physical process that can arise wherever water remains liquid, energy persists, and chemistry has time to organize. Europa frames this possibility quietly. Its ocean does not invite attention. It hides beneath ice, separated from light and weather. If organized systems were found there, it would suggest that life does not require visibility to endure. It requires continuity. On Earth, life is intertwined with constant change. Climate shifts, surface disruption, and atmospheric cycles influence evolution. Europa represents a different context, where long-term stability replaces variability. The contrast emphasizes that life, if present elsewhere, may follow paths unfamiliar to human experience. An everyday comparison helps ground this shift in meaning. A language spoken by a small, isolated community still follows the same fundamental rules of communication. It differs in expression, not in principle. Life beyond Earth would be similar, different in form, familiar in structure. The broader implication is philosophical rather than sensational. Human significance would not be diminished by shared existence. Instead, it would be contextualized. Earth would be recognized as one example of a broader pattern rather than an exception standing alone. Europa's role in this understanding is indirect. It does not promise discovery. It demonstrates plausibility. It shows that environments capable of sustaining organized processes can exist quietly, far from the sun, without surface comfort or visibility. If life exists beyond Earth, The meaning lies not in contact or confirmation, but in recognition. Recognition that the universe allows complexity to emerge in more than one place, through the same physical rules, operating patiently over time.